Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 5. Inverse Interpolation. Inverse interpolation is a numerical technique used to find the value of the independent variable x as input, corresponding to a given value of the dependent variable y as output, when we have a set of data points that describe the relationship between x and y. The inverse interpolation is about reversing the roles of the independent variable x and the dependent variable y. While traditional interpolation typically gives us the value of y for a known x, inverse interpolation lets us find x for a given y. When dealing especially with experimental or tabulated data, inverse interpolation helps solve for an unknown variable, particularly since direct methods are not available. The most frequently encountered problem in science and engineering is to find the value of x for a given y in a set of data. This reverse process is known as inverse interpolation, i.e., it is a process of finding the value of an argument that corresponds to a given value of a function within a tabulated discrete dataset. The simplest method is to find the narrowest interval, denoted by x1 to x2, where the root lies, and apply linear interpolation, just as with bracketing in the bisection method. Eventually, the endpoint values of the interval must have opposite signs. Consider a curved segment that intersects the x-axis between x1 and x2. The equation of a straight line connecting the endpoints is obtained as follows. The line cuts the x-axis at x equals c2. Note that the true root c1 and the estimate c2 are quite far apart. But for curves with small curvatures c1 approximately equal to c2, the linear extrapolation can yield better estimates. Now consider y equals fx on an interval from x0 to xn, which satisfies the inverse function theorem. That is, fx is differentiable and f prime x is not zero. Inverse interpolation requires interchanging the data so that the discrete function is cast as yk and xk pairs for k equals 0 through n. Finding the inverse f for 0 value is then equivalent to determining the root of yfx. Even if the original data is uniformly spaced, the set obtained by interchanging x and y's will not be uniformly spaced. A second, third, or higher order approximating polynomial can give pretty good estimates. The following is an Lagrange interpolating polynomial. Interpolation error depends basically on the numerical interpolation method used. The error of inverse with Lagrangian interpolation is given by the following expression. The derivatives of inverse fx can be calculated in terms of the derivatives of fx, for instance, which implies that the error will be unbounded as f prime x goes to 0. But we can still estimate an interpolant through inverse interpolation, although the inverse function does not exist in the interval from x0 to xn with poor accuracy. When dealing with experimental data, knowing the accuracy of the data is important. If the accuracy of the data is unknown, then the true solution may be off by a large margin even if the root is estimated with high-degree interpolating polynomials. The advantages of inverse interpolation are: the method is simple and straightforward. It requires neither derivatives nor an iterative procedure. A quadratic or cubic polynomial is sufficient in most cases. It can also be used to find the roots of an explicit function in cases where the root-finding methods exhibit convergence difficulties or require a large number of iterations for convergence. The disadvantages of inverse interpolation are: the function, y equals fx, must be an invertible function that allows inverse interpolation. The quality of the estimate depends on how well the inverse function is approximated by a polynomial. Consider the following discrete dataset. Use polynomial extrapolation to estimate the x value at which fx takes the value of 100. The true function is given as follows. In this example, the dataset contains 4 pairs of data. In the case of large datasets, it would be prudent to reduce the dataset to 3 or 4 pairs covering the root. Having said that, in this problem, we will make use of all the data. First, we interchange the data to have f's as abscisses and x's as ordinates, as illustrated. We will adopt the Lagrange interpolation method as it allows a higher degree of fit. The Lagrange basis polynomials are obtained as follows. Once the Lagrange polynomials are found, we can construct the Lagrange interpolating polynomial as follows. Substituting the basis polynomials, along with the numerical values of the abscisses, and expanding, we obtain the simplified third-degree interpolating polynomial as follows. For f equals 100, we obtain 2.10225. Given the true function from which the dataset was derived, we can find the true solution as 2.1243965 as shown. The relative error of this estimate is about 1%. With this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.